area and perimeter here. So we just have a few different objectives that we're going to do. The first one, we're going to find out how to calculate the area and perimeter. And then we're going to use those concepts of the area and perimeter in some word problems, or just applied problems, right? Yeah. So when we look at area and perimeter, the area is just the amount of space that's enclosed in a region, okay? So you can think about it as kind of like whatever area you have enclosed inside of a fence, right? So if we look at this figure down here, the area is basically just how many boxes are in the inside of this rectangle. So the area of this right here is just 12. There's 12 boxes, right? So the area here, so A, is 12. Oops. Okay. And then the perimeter is just how much distance is around the outside. So basically just the fencing that's around the outside of this area. Okay. So in this case, the perimeter here, what we can do is we can just count out how many fence links we need to cover all the way around the outside. So we have one fence link from here to here, so that's one. We have a second one right here, so that's this part. Then there's 3, 4. We can just count all the way up for each link that we use. 8, 9, 10, 11, 12, 13, 14. Right? So we need 14 pieces of fence to cover that perimeter. So our perimeter is 14. Okay. Okay, so now we can do that, but we can do it on maybe different size shapes. So it doesn't just have to be a rectangle. So let's try to find the area and perimeter of each of these. So I'm going to just outline this a little bit better so it shows up a little bit better on the screen. Okay. So this is our area and perimeter. So this is our shape here. Okay. So I have this shape here. So let's find the area first. So let me count the whole number of blocks. So we have 3 whole blocks. So I'm going to label that 1, 2, and 3. And then we have these half blocks, right? So these 2 half blocks together will make our 4th one. So this one and the one in the middle make our 4th block. And then we have a half left over, right? So this is a half. So we have 4.5 blocks for the area of this. And I'm going to label it 4.5 units squared. So since we're talking about 2 dimensions, we're looking at the length and the width. So we're looking at this whole thing. We have to say that it's units squared. So that just means we have 2 different dimensions that we're looking for. Okay. And then my perimeter is just how many chain link fence we have on the outside, right? So if I look from here to here, that's 1. Right? Then here to here is 2. Here to here is 3. Here to here is 4. 5, 6, 7, 8, 9. Right? So it takes 9 to go all the way around. In our perimeter, so we're going to say that's 9. And I'm just going to label it units. So the reason I'm not doing a squared is just because I'm looking for just the length around the outside, right? So we can just kind of like flip this out so it's in one line. So I'm just looking at the length all the way around. I'm not looking at necessarily the length and the width. Okay. Okay. So that's our area and our perimeter, right? And now we can do the same thing with this one over here. So this one right here. So the way I'm going to do this one, we can either use what we did before, or we can kind of do a trick here. So I'm going to do the trick. I think that's going to be a little bit easier. So what I'm going to do is I'm going to cut these diagonal or these triangles off. So I'm going to have a triangle here and a triangle here. And what I'm going to do to make this easier, so I don't have to count the diagonals for the area, is I'm going to imagine moving this triangle and flipping it around and putting it right up in this corner. So I'm going to kind of fill in this spot right here. All right, so I'm just moving this and rotating it all the way around and putting it in this corner. Right. So can anybody tell me what the area is of this right here? So this right here, because I don't have this triangle anymore, right? So what's the area of that figure?
15.
15, right? So we can just count the blocks as 15. Or another way we could look at it is we have 3 rows of 5, right? So we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we can find our area of something by just multiplying the length by the height or the width, right? So 3 times 5, we get 15. Right? So that's another way that we can find the area. Okay, so I'm going to erase a little bit just to make it easier to see again, because now we have to count the perimeter, right? So I'm going to count the perimeter of this. So I'm going to start at the bottom corner. So I get 1, 2, 3, 4, 5, 6, 7, 8. And then this diagonal is 9, 10, 11, 12, 13, 14, 15, 16. So it looks like my perimeter is 16, right? So I have 16 lengths to create this. Okay. Right. Does anybody have any questions on how I found those? Okay. All right. So let's look at this next shape then. So it's a little hard to see on mine, so let me just retrace it here. This one's going to be a little bit harder than the ones we've done before. So I can use some of the same tricks that I had from the last one, right? I can use some of the same tricks. So let's find the perimeter first. So how can I find the perimeter of this? Well, I can just count around the outside again, right? So let's do that. So I'm just going to label each chain link fence or each fence all the way around. And remember this corner, we actually have 2 pieces, right? So we have one here and one here. So we actually have to double count that box. So I have 8, 9, 10, 11, 12, 13, 14, and so on, right? Okay, so I got 34 for the perimeter. Can anybody confirm that that's what they got as well, just to make sure I did it right? Did anybody else get 34 for the perimeter? Okay, well, I don't see anybody disagreeing, so that's good. So I'm assuming that everyone got the same thing. Okay, so now we found the perimeter. Now we can find the area of this, right? So instead of, maybe rearranging it like we did on the last one, I'm just going to split these up into easier sections to count, okay? So what I'm going to do is I see this huge rectangle right here. So this huge rectangle. So I'm going to split it off and count that rectangle. So I'm going to make a line right here. And then I'm going to do the same thing up here. Right? So I just have this nice rectangle that I can count. And then I can do the same thing down here, right? So I'm just going to split this up. So I have 4 different rectangles that I need to count. I have one up here. So what's the area of this tiny rectangle up here? Well, we can just count how many boxes there are, right? Yeah, it's just 2. So I'm just going to write a big 2 there. How can we find the area of this biggest rectangle? So how can I find the area of this biggest rectangle? So the first thing I can do is I can just count on every single box, right? Yeah, or what I can do is just multiply how many rows by how many numbers are in each row, right? So kind of what Kevin was on the track of is we have 1, 2, 3, 4, 5, 6, 7 rows, right? And we have 5 blocks in each row, right? So we just have 5 times 7. So we get 35 right here. And so our area here is just 5 times 7, which is 35. Yep. And then we can do the same thing for this one. So we have 2 times 4, which is 8. And then 2 times 6, which is, or 2 times 3, which is 6, right? So my area is just adding all those numbers together. So 2 plus 35 plus 8 plus 6, right? So my area here should be 51. So my area is 51. Okay. All right. So we found our area, we found our perimeter, so that's good. We can do the same thing on the next one, right? So the next one says, find the area and perimeter of the following figure if the slanted lines each have a length of 5 units. So these slanted parts, they have a length of 5, right? So I think the easiest thing we'll do, so what we'll do first is find the perimeter. So we have 5 and 5, so all we just need to do is count the perimeter around the outside here. So maybe I should fill that in just so it's a little easier to see. So if I find the perimeter, well, I can just count 1, 2, 3, 4, 5, 6. So I know that I have a length of 6 up here, and I know that the bottom side is the exact same amount of length as well. So instead of counting those out, I'm just going to label it 6 down here. Okay, and then now I can label this side right here. So I have 1, 2, 3, 4, 5, 6. So this is also a length of 6, right? So maybe instead of labeling each one like this every time, we can just give each side a length of 6 in this case. Okay. So my perimeter is just adding up all 5 of those numbers. So we have 5 plus 5 plus 6 plus 6 plus 6. Okay. And we should get 28 for the perimeter. So that's just the sum of all the side lengths. Okay. And now we can do something similar to what we did up here, right, to find the area. So let's split this up into 2 different things. So I'm going to draw a line from here to at the bottom here. So now I have a 6 by 6 rectangle, right? So 6 times 6 is 36. So the area of this is 36. And then now I need to find the area of this over here. So I'm going to use the same trick that I did on the last page. I'm going to split this right down the middle here. And then I'm going to rotate this triangle here, and I'm going to move it up here. So I end up with a little box like this, and I have a 3 by 4 box, right? So the area is 12 of this, meaning that the area of this triangle here is going to be 12 as well, right? So my area is 12 plus 36, and 12 plus 36 is 48. So the area is just this part added to this triangle up here. Okay. Anybody have any questions on this page? Okay, all right, so we'll go to the next page then. So when we have 2 shapes that look really similar, or that look almost like the same thing, we call them similar triangles. So they have the same shape, but not necessarily the same size. So what I mean numerically is that the ratio of the corresponding sides are always the same. So what that means is that if I have something like this example that they give down here, I have two different ones, and they're not the same size for sure, but it looks like I have some kind of ratio or some kind of proportion going from this one and scaling it up to this one. Well, I can see going from 12 inches on the longest side to 24, I'm multiplying by 2, right? So if I multiply by 2 on the bottom, if I do that on every other side of this smaller one to scale up, well, we get the lengths of each of the sides over here. So we know that they're similar. This one's just half the perimeter of the one of the bigger one, right? So they're similar because when they're oriented in the same way. So they just flipped this one, or they flipped the bigger one over, so they look like the same thing. They're in proportion, or they have that same ratio on each side. Okay? So when we have similar triangles, they have the same shape, but not necessarily the same size. And one thing, if they have the same size, so if we had like another big one, we would call those congruent. So these two right here, they are congruent triangles. So I'm just going to write congruent, and that just means they are the same triangle, or the same shape rather. So they're the exact same shape. So I would just say maybe same shape and size. So that's what a congruent shape is. So there are two shapes with the exact same size and shape. Okay, so we can use this example to kind of bring home the point. So this one says, the triangle shown below looks similar because they have the same shape. So it says to verify this, we need to check that the corresponding sides are proportional. So I already oriented them in the same way, so we don't have to like flip them over or move them or anything. But it says use the ratios and proportions. So what I'm going to see is that going from this short side, so this 13, to this bigger side, I have to multiply by something to get from 13 to 58.8. And the way I can do that is just divide these two numbers. So if I do 58.8 divided by 13, so that's this ratio that we're getting down here. I just used a colon instead. That's the same thing as saying that it's equal to some number over 1. So basically what I'm saying is for every 1 inch that I have for these 13 inches, I have how many inches for 58.8. Okay? And the way I can find that is just dividing these two numbers. So if I do 58.5 divided by 13, we get 4.5. So what I'm saying is for every 1 inch on this 13-inch side, I have 4.5 inches on this 58.5 diagonal. Okay. So if the triangles are similar, I'm going to have that same ratio on all three sides. Okay. So if I do 54 divided by 12, so that's just the next shorter side. If I do 54 divided by 12, I'm getting 4.5 again, right? So I'm getting that same exact ratio that I did with the longer side, right? And then I can do the last thing with the shorter side, right? So I have 22.5 to 5. So that's just comparing the two shorter sides. And that's equal to something to 1. So for every 5 inches, or for every 5 inches, I should have 22.5 inches. So for every 1 inch, I should have something. And the way I can find that is the same method, right? So I just divide the bigger number by the smaller number. So 22.5 divided by 5, we get 4.5 again. Okay. So since all these ratios are the exact same thing, that means that these triangles are definitely similar. So they have to have all three of the exact same ratio after you simplify it down. Okay, does anybody have any questions on similar triangles? All right. All right, so we'll go on to, I think the last example here then. So this one says, the following two triangles are similar. So we're given that they're similar. So it says find the lengths of the two remaining sides of the larger triangle, right? So let's change this triangle and orient it like this one. So I think what I'll have to do is just rotate it by 180 degrees, right? So this bottom should match up with the bottom here. So I'm going to redraw the triangle here. I think it goes back maybe just a little bit, something like that. So I'm just redrawing this triangle over here. So I know that the really short side is 3. The longest side is 6. And then the other one's 5. Okay, so I'm just redrawing that triangle over here. So I want to use the ratio to find the lengths of these longer sides, right? And the way I can do that is we know the lengths of the bottom parts of the triangle, right? So I know that I have 5.7 over 3 equals some number over 1. So for every 1 inch that I have on the smaller triangle, I have some amount of inches on the bigger triangle. Okay? So what I'm going to do is just do 5.7 divided by 3. So I get 1.9. So for every inch that I have on this triangle, for the lengths of the sides, I have 1.9 inches on the bigger triangle. Right? So does anybody know, how can I find the length of this longer side using this ratio in the length of our longer side on our smaller triangle? So what do I need to do with the number 6 and the number 1.9? So what do I need to do with 6 and 1.9 to get to the bigger triangle up here?
Just multiply.
Yeah, I just need to multiply them, right? So all I'm doing is just scaling it up. So I do 6 multiplied by 1.9. So 6 multiplied by 1.9, we get 11.4. So the length of this side is just 11.4. And then we can do the same thing over here, right, on the shorter side. So we get 5 multiplied by 1.9. We get 9.5. So that's just the length of that shorter side. We're just scaling it up. So for every 1 inch that I have here, I have 1.9 inches on the shorter side. Okay, so that takes care of that. And then we already talked about the congruent part. I forgot it was later in the notes. So if two triangles or two figures have the same shape and size, they are congruent. All right. Does anybody have any questions on this last page? Okay. If you don't have any more questions for me, you are good to go for today. If you do have any questions, feel free to stay and I can answer them for you.